Okay, hi again. Now that we have welcomed you to the course, we have said a few words about what algorithmic thinking is about. We will start with the actual material in the course, and we will start with the very first problem that we will see and deploy or employ algorithmic thinking to solve that problem. And the problem is going to deal with something with a phrase that you probably have seen or have said, or a phrase that you have heard from someone or have read it somewhere, which is, it's such a small world. I have said it many times. You probably have said it, or again, have read it somewhere. You travel to a different country. You see someone who turns out to know someone that is your cousin or your friend, and so on, and they say it's a small world. So in this part of the course, we are going to talk about that small world statement that we make. What is a small world? What does it mean? What does it imply? What should we care about it? And how do we test if the world is really small? Okay? So in this part of the course, we are going to use algorithmic thinking to reason about the world, if it is small, and how do we decide if it is small, or how do we test algorithmically if it is small? Okay? Now, what does it mean to say that the world is small? We usually use it in the context of who knows whom, right? In the sense that, again, I travel to country X, I meet a person there, and that person, we start chatting, having a conversation. That person all of a sudden mentions another person that turns out to be my colleague or my cousin, and so on. So we usually think about the issue of small world in terms of who knows whom. So if you think about individual X knowing Y, Y knowing Z, Z knowing W, and so on, the question is, does X know W, for example? And if I take any two individuals, what is the chance that they are connected through a very short path? Okay? So when we talk about small world, and we're talking about the world as the individuals and who knows whom, then when we talk about small world, we are basically saying, if I take any two individuals in the world, what is the shortest path that connects these two people in terms of who knows whom relationship? Okay? Now, why do we care about the small world? Of course, this is an algorithmic thinking class. It's not about, let's just try to quantify what people mean by it is a small world. No, the world being small is actually a phenomenon that doesn't just apply to the world as individuals and their relationships. It applies to a network, for example. You can basically look at a computer network and say, if I take any two nodes in that network, how far apart are they? If I take two nodes at random, how far apart are they? If I take any kind of connectivity map, for example, of proteins in the cell, if I look at your cell and I map all the proteins and their connections, if I take any two proteins at random, how far apart are they in terms of connections? Okay, protein A talks to protein B, B talks to C, C talks to D. So we have a path of length 3 between A and D. How far apart are they? Now, this phenomenon of small world, again, that applies to protein networks, to computer networks, to networks of humans and individuals and how they know each other, has great implications in many areas. For example, if we have a small world phenomenon or small world effect in a certain system, like if every individual is connected to every other individual by a path, by like at most 3 other individuals, then you can think about information flowing through that population very quickly. If someone starts a rumor, that rumor is going to spread very quickly. But for more interesting applications, for example, in the area of epidemiology, if the individuals in a city, for example, are connected so tightly that we have a small world effect, that we have between any two individuals, we have such a short route, then if someone gets infected with infectious disease, then there's also a very good chance that that disease is going to spread through the community very quickly. So the small world phenomenon, it started basically by thinking about how people are connected and how far apart are any two individuals that we choose at random. But its implications and its interest are way beyond just looking at individuals in a society. So we care about this, And when we have a system of interconnections, we are interested, one of the things that we are interested in knowing, does that system exhibit the small world effect? Okay? One of the main experiments, or the first experiments that were done to look at whether humans or individuals are connected very tightly, in the sense that any two individuals are connected by a short path, was done in the early 60s by Stanley Milgram. And you can look up, for example, the Milgram experiment. It's a very famous experiment. It was done in such a low-tech fashion that they were basically mailing letters among individuals, and they wanted to see how long it takes the letter to reach from person A to person B, even though A and B have no knowledge of the relationships of the individuals in the community. However, our access to data and our access to information technology has improved tremendously since the early 60s. So today, we have access to very large scale social data from Facebook, from instant messaging, from Twitter, from emails, and so on, that will allow us to ask these kind of questions at a much larger scale, from much large scale data, and in a much more systematic way. Instead of us mailing letters now among individuals, we can now go and mine sources of data from Facebook or Twitter, again, or emails, for example, and try to quantify that question and try to understand, is the world really small? Okay? So the first thing is, we need to understand the problem. Again, remember that we want to employ algorithmic thinking. We need to understand the problem here. So let's assume that we have access, for example, to all the Facebook data. Okay, so we have information about all the individuals that have accounts on Facebook. We have also all the information about who's a friend of whom. Okay, we would like to know, understanding the problem basically tells us that we would like to understand if, using Facebook data, the world is small. Okay, so what that means is that if I look at the Facebook data and I take any two accounts in the Facebook network, what is the distance of these two accounts? If I take any two accounts at random, again. So the problem in this case is actually not very hard to understand. We have all the Facebook data. We need to see if that Facebook data exhibits small world effect. Next, we move next to the formulation phase, and we need to think now about how do we formulate the input to the problem. Now, it makes sense when we look at, again, individuals and their connections, that we have a representation that says, okay, I have here this individual 0, individual 1, individual 2, 3, 4, and so on. Again, when we look at the entire Facebook data, we have many more than 5 nodes. But for the sake of illustration, let's assume that we have 5 accounts for 5 individuals. Then we have these 5 individuals. In addition, we know also from these individuals who's connected to who's a friend of who. So for example, 0 is a friend of 1, 0 is a friend of 2, of 3, and of 4. 1 is a friend of just 0. 2 is a friend of 3, and of 4. These are the connections. So if I take a snapshot of Facebook, this is what I get. I have 5 individuals. This is how they are connected on Facebook. So this will be the input. And in this case, it makes most sense to think about the input in terms of a graph, again, nodes and edges, because the system is amenable to a representation with graphs. Okay? Once we have this input, what is the output? How do I test the small world effect? I have to look at, for every pair of nodes here, I need to ask the question, what is the distance between these nodes? Okay? So one way to look at this is by producing what we call a distribution of the pairwise distances. What is the distribution of pairwise distances? I have to tabulate all the pairwise distances here. I have to say, I have to look at every pair of nodes, node 1 and 2 nodes here, and I say, what is their distance? Since we are looking here at who knows who, we don't have a weight to the edge. We are not asking who knows who best or communicate 5 times a day or anything like that. All we are saying is that who knows who. So now when we talk about the distance, the next question we ask, what is the distance here? In this case, basically, what is the minimum number of connections that will take me from individual I to individual J? So the distance between nodes 0 and 1 is 1. They are connected by 1 connection. From 0 to 2, it's 1. From 0 to 3, it is 1. From 0 to 4, it is 1. 2, from 2 to 0, it is 1. Actually, we can look at individuals 1 now. 1 to 0 is 1. From 1 to 2, it is 2. From 1 to 3, it's 2 as well. From 1 to 4, it is 2. And so on. Once I have these pairwise distances for every pair of nodes, their distance, I can tabulate this and say, okay, how many pairs of nodes have distance 1? Then I can look at all of them. I can count them 1, 2, 3, 4, 5, and so on. Let's assume we have 7 pairs that have distance 1. Then I put a bar here. How many pairs of nodes are distant 2? It might be 4, for example. And I put a bar. How many are distance 3? This, and so on. This is what we call the distribution. Distribution of pairwise distances. This distribution is going to tell me whether the world is small or not, whether this Facebook network exhibits the small world effect or not, because I can look at it and say, for example, if this is the entire distribution, I will say any 2 individuals you take at random, they are connected by a path of length 1 or 2 or 3, which are very short. In this case, actually, they might not be too short because this is the number of individuals is already 5. But you get the point that if I take this input and this output, basically, I have formulated the problem cleanly, and it will allow me to answer that question whether Facebook network exhibits small world effect. Okay? So this is what we basically mean here when we say that this is the formulation of the problem, and we formulated the problem as a graph theoretic problem. It's a problem that involves graphs. Okay? So now we are going to move to graphs, what graphs are, and some basic concepts.